Welcome back to the microwave spectroscopy. In the previous video, we talked about the moment of inertia, I, and the rotational constant, and we see that knowing B, we can obtain I, and then the bond distance in a diatomic molecule. So how do we relate I, B, and the rotational spectroscopy? We know that I is related to the molecular structure and that we can obtain I from B. And B, how do we get that? We obtain B from the spectrum. So how do we get the spectrum? We get the spectrum by considering another selection rule, which is the specific selection rule for J this time. If you remember, we have the general selection rule. And the general selection rule is that the molecule must have a permanent dipole. Now we are going to consider the specific selection rule for J. The reason for this is that it helps to get a mathematical relationship, and then from there we can obtain B. So in addition to the molecule having a permanent dipole, for the J, remember, J is the rotational quantum number that characterizes the energy level. So it is required that if you're going from one energy level to another energy level, J can only change by +1. So for absorption, you can go from J equals 0 to J equals 1, or J equals 1 to J equals 2. It can only change by unit of 1. And for emission spectrum, you can come down from 1 to 0 or from 2 to 1. 0 is the ground state, so you're not going down to anything from 0. In the presence of external electric or magnetic field, now this also affects rotational states, much like they affect atomic states. The other selection rule that is in place is Mj equals to 0 plus 1. And Mj talks about the different directions in which J can point. It's similar to the azimuthal, the magnetic quantum number ML for atomic systems. So let's look at our energy levels. If we recall, we said that the energy level, this F of J, is a convention for rotational energy level state, and then we are writing it in terms of wave numbers now. Okay, so we recall that the energy level is represented by J into J plus 1B, B being our rotational constant that equals h squared over 8 pi squared I in joules. So with this, we can construct energy level. So if J equals to 0, definitely, because you are going to multiply everything by J into J plus 1B, so anything you multiply by 0, so that's 0 into 0 plus 1B, that's 0. So what that implies is that your molecule in the ground state does not rotate. There's no rotation in the ground state. So if J equals 1, and we put it in that equation, so we have 1 into 1 plus 1, that's 1 plus 1 is 2, times 1, 2b. If J equals to 2, you can continue to calculate it. 2 plus 1 times 2, that's 6, that's 3 times 2, then 3 plus 1, that's 4 times 3, that's 12b. And we continue on and on like that. We can represent this in an energy level diagram. So here we have calculated from J equals to 0 to J equals to 5. So J equals 0, energy level, energy is 0. J equals 1, energy is 2b. J equals 2, energy is 6b. So what comes up is that we notice that as J increases, the energy required, the energy spacing increases. It's not equal, so we may not have equal probability in terms of energy, equal probability of jumping from one energy space to another. So let's consider transitions, remembering the selection rule of delta J equals plus or minus 1. So if we try to go from J equals 0 to J equals 1. So in the ground state again, the molecule is not rotating. So from the ground state, we're considering absorption now. From the ground state, J goes from 0 to J equals 2B. The energy required is about 2B. So it's just 2B minus 0. So if we consider the transition from J equals 1, that's the first excited state, to the next state, J equals 2, then the energy required for that is 4B. So what this means is that if you pass energy equivalent to 2B, we have transitions from 0 to 1. If you have energy equivalent to 4B, we have transition from 1 to 2. So if you have a mix of energy that's equivalent to 2B and 4B, we will have simultaneous excitations from 0 to 1 and 1 to 2. So if we look at the order, J to 2 to 3, transition J equals to transition to the state J equals 3, we have 6B. So that's 12B minus 6B. So, and I think if we continue from 3 to 4, that's about 8B. From 4, and it goes on and on. So 2B. So if you pass, and if you have a sample molecule and you've passed energy equivalent to 2B to 4B, we have all these that are going to be absorbed from the spectrum. So before I leave this slide, there's one thing that I quickly want to share. This 2B, 4B, there's a general formula for it. So you have a transition from the energy absorbed, you have a transition going from J double prime to J prime. Now in microwave spectroscopy, J double prime is often used to indicate the lower state of transition going to a J prime upper state of transition. So we need to input this into the expression for each energy level. If you recall, it's J into J plus 1B. So this is the energy absorbed will be the energy level going from the upper state J prime to J prime prime to plus into J prime plus 1B minus the energy of the lower level J prime prime double prime into J double prime plus 1B. So if we solve this, we arrive at this general equation, and if we compare this to what we have, so from 0 to 1, that's 2B into 0 plus 1, that's 2B. From 1 to 2, so recall, this is the J double prime of the lower state, so we're using that as the substitution. So from J to 1, we have 2B, that's from here, into J prime prime as the lower state, which is 1, plus 1, that's this one, so we have, that's 2 times 2B. Similarly, if we're going from 2 to 3, so we substitute for 2 in here, plus 1, that's 3 times 2B, 6B, which is equivalent to 1, what we have here. So this is 0 to 1, 2B, 1 to 2, 4B, equivalent, 2 to 3, 6B. If you can verify the others as we like. Okay, so back to our spectrum. A quick recap: 0 to 1, we have absorption from 2B, 4B. So if we put this on the simulated spectrum that we expect, this is our energy, bringing back on this slide. So if you look at it, you shine energy into your sample. So you have 2B absorbed from 0 to 1 transition, 4B from 1 to 2 transition, 6B from 2 to 3 transition, 8B for the 3 to 4 transition, and then we have it up to 19B in this picture. So energy absorbed 2B, 4B, 6B, 12B, and so on and so forth. What we notice is that the separation between the energies that are absorbed, 2b and 4b, that's 2b, the separation between each peak, 4b and 6b, 2b, 6b and 8b, 2b. So you have a separation of 2b, 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 2b. So if you have a spectrum, you have lines that have been shown, and then the spectrum, the lines are approximately 2b apart. That's from what we have discussed. So what's important that is these states, vibrational states, are usually populated because they are small. So we have several transitions taking place at the same time. This is unlike vibrational and electronic states where you have only one transition that could take place. Usually for those ones it's from the zero state, the ground state, to the first excited state. But here we can have several excitations, and that's why we can have 0 to 1, 1 to 2, all happening at the same time. So this is an example of a spectra that was obtained in the lab. So we see the peaks are at an equal distance apart. So we're not going to worry about these little peaks. That's from some form of noise. So this is a J to 3 to 9 transition, 3 to 4, 4 to 5, 5 to 6, 6, and so on and so forth. If we look at another sample obtained in the lab for hydrogen chloride, it's for carbon monoxide. It's a diatomic molecule. This is also another diatomic molecule. So what we notice is that there are several lines as seen, again because several states are occupied, because rotational energy levels are close and are of low energy. But more importantly, the separation between our lines, they are approximately equal, and they are about 2b apart. So we can easily obtain our B from the spectra related to the moment of inertia, and then we can calculate the bond length. So a sample example is given. The transition J equals 0 to J equals 1 for carbon monoxide, so carbon trioxide, is observed at 3.84235 wave numbers. Note that it's very specific, the carbon monoxide, carbon 12 and oxygen 16. That's because isotope effects affect the rotational spectra greatly. Now, given the atomic mass of carbon 12 and oxygen 2 as given, calculates the bond length. Now we know that when a transition occurs going from J equals to 0 to J equals 1, the amount of energy absorbed is 2B. And from the question, that's the value. So we can calculate B as 3.84235 divided by 2 and gives us 1.921175. From there we calculate our I, h over 8 pi squared BC. C, because we're using this formula because B is given in wave numbers. Substituting all that, we have our I equal to a particular number which is not on the slide. And we also note that we have to calculate bond length. I is also equals to mu r squared. Mu, that's the mass of carbon, mass of oxygen, that's the reduced mass, effective mass, divided by mc plus mo. So that's 12 times 15.994 over 12 plus 15.994 multiplied by our conversion factor. We always need to convert from atomic mass units to kilogram. So we can calculate I, we substitute our values from I and mu. R, we can calculate R, rather R is the square root of I over mu. And we have it as a 0.1131. Okay, see you in the next video.